So let's continue where we left off. So the goal, so last time we wrote down this inductive scheme, and we somehow convinced ourselves that if we could somehow close the scheme, then we would have a proof of the theorem. So let me just write down somewhere this inductive scheme. So we're going to construct incompressible vector fields VQ and Reynolds stresses traceless ones RQ. So divergence of VQ is 0. dt of VQ plus the divergence of VQ tensor VQ plus the associated pressure, divergence of the stress. And these things have to satisfy certain estimates. So let me write down the estimate. Stress satisfies L1 bounds, but of course it comes with derivatives. Just rewriting what I wrote down on the board last time. Same thing in L infinity. Okay, so the amplitude of the stress, so when M and N are 0, it's going to be called delta Q plus 1. I'm going to maybe recall the parameters here. So lambda Q is A to the B to the Q, and in particular, lambda Q plus 1 is lambda Q to the B. B is a number close to 1. Delta Q is lambda Q to the minus 2 beta. And beta, we have seen last time, actually measures the regularity exponent. So that's the meaning of the letter beta. We haven't yet seen meanings for the letters A or B. So in L1, this is of that size, in L infinity, it's of that size. And then cost of derivatives, these derivatives cost that much. And the material derivatives do have, remember, the material derivative is dt plus vq dot grad. They have different costs in L1 and in L infinity because the cost is essentially the Lipschitz norm of VQ, and that has different costs. So it's tau Q minus M, and this is lambda Q to the M. And let's remind ourselves that tau Q inverse is lambda Q delta Q to the 1/2. I think that's all I need to box here. And we're going to have estimates for the velocity as well, too, and in L1, not for the velocity, for the velocity increments. So I did forget to introduce one more notation. WQ plus 1 is VQ plus 1. Propagate things for the velocity increments. So in L2 and in L infinity, they have size square root of the respective stresses. So it's delta Q plus 1 to the 1/2 and 1 to the 1/2. The derivative cost is lambda Q plus 1 because it's the higher frequency. And the material derivative cost, in a sense, has nothing to do with this. It has to do with VQ. So it's the same as the other one. And this is meant to hold up to some ridiculous level of N and M that we won't even attempt to quantify. All right. So I should make a little comment that these vector fields, gradient and dtq, do not commute. It's not equal to 0. In fact, it's gradient of vq dot grad. It's a first order differential operator. And as you can imagine, this is not going to fly because they don't commute. So in fact, you don't propagate this. You propagate all words of length m plus n in those letters because they don't commute. Oh, thank you, Hiro. Now I have 3 coffees. Thank you, Hiro. I don't have COVID, but I may get a heart attack. Okay, so you need to propagate not this, but all possible words in those 2 letters. Okay, and they're non-commuting vector fields, so it's kind of annoying. Okay, hope somebody convinces me not to erase that board today, because I would hate to have to rewrite that. The first step is we have discussed last time that we have some kind of intuition for an ansatz. And now let's make that intuition slightly more clear. But it's, of course, it's not going to be right. So you keep on building the complexity of the ansatz. So remember that the whole point is that the new stress. Let me maybe remind you the design problem we're facing. We have the new stress plus some pressure gradient, which I refuse to write. is equal to dt cubed material derivative of the perturbation plus the perturbation dot grad old vector field, and then the nonlinear term and the old stress. Okay, so the design problem is, given VQ and RQ, remember VQ is just the sum of the W's, right? Because telescoping series. Given VQ and RQ satisfying the bounds that follow from this, design WQ plus 1 such that design WQ plus 1 within these constraints, such that RQ plus 1 satisfies that thing with Q replaced by Q plus 1. That's the design problem we're facing. And so the first guess that WQ plus 1 is going to be like a sum of some amplitudes on the slow objects and some fast oscillating indexed by Q plus 1, just to emphasize that it's fast. If you remember that we discussed a little bit yesterday that if you were to make an ansatz, that you had a master function which depends on this and this, a fast time and a fast space, essentially we're doing separation of variables. We're saying, let me put all the fast stuff in here. Let me not say yet what it is, and let me put the amplitudes in there. And this is a sum because maybe I need more than one. And I'm going to index them by a Greek letter, xi. And I'm going to tell you what the summation over xi represents. Okay, but maybe I'm going to need more than one amplitude and one fast function. So this fast function, I already know something about it. These objects are slow, right? We already have, by induction, that they satisfy the correct estimate. But we also know that these things, the derivative can cost at most lambda q plus 1. So the x frequency, sorry, the gradient x frequency is at most lambda q plus 1, because otherwise we would violate this. Moreover, the material derivative frequency is at most tau q inverse in L1, lambda q. So we have some constraints on these fast building blocks. These are the constraints, and they're just coming from here. These things are sometimes referred to as building blocks. The reason is that these are the fast objects which you modulate with the slow ones, and we have discussed yesterday that the fast objects essentially should be stationary solutions of 3D Euler, right? Because if all the fast derivatives hit this guy, we better get 0 to leading order. So it needs to be to leading order a stationary solution of order. So let's discuss a little bit of a few properties of the building blocks, considerations mentioned yesterday. So the first one, I mean, we've already written some considerations, these two, oscillation constraints. Should have 0 mean, because in the end we want the solution of 0. We want them to be stationary solutions of Euler to leading order. Let's say that the divergence of this guy is a pressure gradient. That's the condition that they're stationary solutions of Euler, along with incompressibility. And I think we have discussed one more quite important feature yesterday, namely that the interaction of fast things here is the only thing that produces a slow object in this construction. And so you would really like that the fast the slow part of this fast interaction gives you something non-trivial, because otherwise you're not going to be able to cancel this term. We've talked about this yesterday. The slow part of two fast objects is just the mean. Okay, so we're going to have a condition on the mean. This is the first time that this index xi is going to appear. So I'm going to make this to equal xi tensor xi. You'll see why in a second. And I should tell you now that xi is an element of S2 Q3. And for the moment, that's all that matters. It's a unit vector with rational. Okay, so these are just the basic constraints on these building blocks that just follow simply from our considerations from last time. I should add one more on this board, because otherwise, but it's not going to fit on the board, so I need to switch. A lot of the discussion in the previous lectures was about how LP spaces are not quite the same as Hölder spaces. And we have referred to this fact as intermittency. And because of the result of Constantine O and TT, we know that if we want to get H1/2 solutions, in particular regularity above 1/3, we can't just work with homogeneous functions, C alpha functions. We have to work with functions that scale very differently in different LP. They have concentrations, not just oscillations. The way to measure concentrations, or a way to measure concentrations, is to say that these building blocks, they don't occupy the whole torus, occupy a very tiny subset. They're concentrated. So for the moment, let me just write this down. So this guy occupies, which is much less than 1 within the torus. Of course, they have to be periodic. I'm not even going to write this. Everything is periodic, right? And the way we're going to measure this volume is by a new parameter, which is called the intermittency parameter. So RQ squared, where RQ is the intermittency parameter, concentration. We've just made this up for the moment. We first of all have no idea what this RQ should be. It's not in this box. It doesn't have any natural choice so far. We just said it has to be concentrated, because if it's not very concentrated, we just know a priori that nothing's going. So by the way, if you are concentrated to that size and your derivative costs that much, you kind of know actually what all LP spaces should be bounded by, right? Let me write this down. So as a consequence, the nth derivative of this guy in LP would be less than 1. Obviously, the derivative is going to cost what it's going to cost. So what is the LP norm of such a building block? So if you have an object which is concentrated to a volume of size RQ squared, it's periodic. Compute its LP norm? Of course not, because I didn't tell you how I normalize it. Is it normalized to have, I don't know, mass 1, or is it maximum 1? How do you normalize this object? Well, the normalization is implicit here. Because if you take the trace of W tensor W, that's the integral of the trace is exactly the L2 norm. And the trace of this is the modulus of xi squared, but it's an element on S2. So that's 1. So I've implicitly written here that these objects are L2 normalized to unity. So whatever I'm going to write here, but now I can compute. If I have a function which is concentrated on that set, and it's L2 normalized to size unity, then I know what all LP norms should equal, assuming this function is beautiful. So it's a bump. I'm going to write one more bullet, which at this moment, it may seem unjustified. Like it seems like I'm imposing a lot of things on this without even knowing it exists. And I'm going to write one more. The justification may come in a bit later. You see, the increment is a sum over such objects. But in my equation, I have products, nonlinear functions. When I do nonlinear functions, like just the product, I'm going to get W sub xi interact with W sub xi prime for xi and xi prime not equal to each other. For reasons that are going to become apparent only later, I would like different building blocks to not talk to each other. I'm going to write down something which, again, for the moment may not seem justified, but I want the spatial support, actually space-time, of two different objects to be the empty set. We haven't even discussed what this xi represents or anything. So I would really like these things to not see each other. So at this point, you've seen me write a lot of bullet points. I require a lot of things about this object. And before, yes?
Really, for any psi different from psi prime, you will have these things.
Yes. So as long as their index is different, I don't want them to talk to each other. Subset. Okay. It's a small subset. Okay. So in particular, a set of 6 elements.
Okay. Okay.
And why a set of 6 elements? If you think about what we're doing here, we're trying to use the low frequency part, which gives you this rank 1 tensor, to cancel a given stress, RQ. RQ is a symmetric stress. It has 6 degrees of freedom. So how many rank 1 tensors should I need to write any stress as a linear combination of rank 1 tensors, well, 6. And unless I choose them really stupidly, like parallel to each other or anti-parallel, if I choose them at any kind of non-trivial angle, I will span the set of symmetric 3x3 matrices as linear combinations of rank 1 tensors in there.
So what do you specify Q3?
It's going to come up right now. It's going to come up right now. That's actually very important. It's this. This is where Q3 matters. Okay, so before we even discuss, is this really useful? Let's discuss, does this even exist, right? If it doesn't exist, we shouldn't even talk about it. So do such objects exist? And the answer is yes, of course, because otherwise I wouldn't be giving this talk. So let's start off easy. If I take in 3 space dimensions, there's a ghost pushing this board around. Can you please talk to the ghost, Jessica? So if you take in 3 dimensions a straight tube, straight cylinder, and you write any function of x1 and x2 times E3, smooth function phi. This is a vector field. Is it incompressible? Well, yes, because the divergence of that object is d3 of phi, which is 0. Does it actually solve Euler? Yes, it does, because phi E3 dot grad phi E3 is E3 phi d3 of phi, so that's 0. Not only does it solve Euler, it solves Euler with 0 pressure. Is a solution of 3D Euler with 0 pressure. And if I take phi to be compactly supported, I can make the whole solution to be compactly supported. Well, there's a caveat. It's extended to infinity. Can I make it of 0 mean? Yes. I can just make sure that this is like the profile. So there's flow in that direction, and there's also flow in that direction. Like a tube in which there's some kind of water, and it's flowing in many directions, but it's parallel to this axis. There's no movement in any non-E3 direction. And okay, is this a periodic object? It points in a direction E3. So let's just check if psi were equal to E3, does this satisfy all the properties I want? So let's go through the things. Frequency constraints. Okay, so I should really make sure. What is the only gradient appearing in this vector field? It's in that direction, right? It's in this plane, sorry. All gradients point in that plane. So if I want to make sure that gradients cost at most lambda q plus 1, all I have to do is make the thickness of the tube proportional to lambda q plus 1, right? Inverse. At this point, there's no time, so let's not even mention time derivatives yet. Okay, so do we have the frequency constraint? Yes, we have. 0 mean? Yes, we have. Is it a stationary solution of Euler? Yes, even with 0 pressure. What mean does it have? No, let's talk about concentration first. What volume in the sphere does it occupy? That's a problem, because if I just take this thing, it's going to occupy, if it has that thickness, extremely little volume. It's going to occupy lambda q plus 1 inverse volume, right? Because there's just one tube of this thickness. These are 2 dimensions. So the whole volume is lambda q plus 1 to the minus 2. That's a tiny number. Nobody told me that RQ is lambda q plus 1 inverse. So how can I make this be exactly equal to RQ, no matter what I choose RQ to be? So then what do? Well, you take your periodic box, divide it into boxes of width. Let me just draw 3. Of each one of these boxes is lambda q plus 1 RQ, that's the RQ, inverse. Okay, so these are boxes, cubes. I've subdivided it. Okay. Now I'm going to take this tube, which has that width. It points in the direction of E3. And I'm going to make it periodic, but not with respect to the unit box, but with respect to these tiny boxes. So I'm going to periodize this little thing. I'm going to keep its width, okay? Again, I'm going to periodize it to that scale. So essentially, we're going to have these little things like they're everywhere. Going to be motion in all of them, and they're periodized. Now you can do the computation. If you have periodized something of this width to that scale, the total volume occupied by these objects, which, they're everywhere, right? Exactly equal to RQ squared. By the way, by periodizing it, did we screw up the frequency? No, because the frequency is still, at most, the width, inverse width of this. Okay? So we didn't screw anything up. So we have our volume constraint. How about this? This is an integral over the box, right? If I make sure that it's periodic with that smaller box, average value over the big box is exactly the same as the average value over the small box. That's called periodicity. So what constraint do I need to impose on phi such that I have this property with E3 tensor E3? I just need to ensure that the mean over the small box of phi over the small torus. What does that mean? I specified a width of this object, and I have specified its L2 norm. So it's a bump. So if we were to look at the profile at this object, it's a bump. This is lambda q plus 1 inverse. And the height, there's a unique one if you chose your profile such that you get this. There's a unique height. It's pretty high, by the way. It's RQ inverse. Right, Matt? It's RQ inverse is the height.
Yeah.
Yeah, okay. Just I wanted to check. So if RQ is a tiny number, RQ inverse is a high number. Okay. So it's these things occupy little space, but they're big. So they happen infrequently, but they're huge. And because of that, they still can carry L2 norm. In spite of the fact that they have small support, they can carry huge L2 norm of size unity. So now comes the question of this one. So if this direction vector psi were to equal E3, I have satisfied all the properties except for the box one, which refers to two different psis. Now, take 6 of these psis. The fact that they are not just psi is a direction. The fact that psi is not just an element on S2, but also in Q3, means that these things can be periodized, because otherwise they will be dense in the torus. And if they're dense, you're never going to make them not intersect. So they better be periodized at some kind of rational angle. So I have another one, which is maybe sitting in here, and it's periodized, the same thing, etc. And it's also everywhere in the torus. So is it possible that I can have 6 of these not see each other? And the answer is, of course, yes, because in 3 dimensions, lines can miss each other, right? Slightly thickened lines can also miss each other. And if you just make sure that the rate of periodization, which is the denominator in this rational number, is sufficiently nice. So these are our building blocks. So they're objects which point in the direction psi. They're multiplied by a density which points only in the directions orthogonal to psi. They're periodized to this scale. And they have in total this volume. So these are the objects we're going to work with. You don't. And in fact, that's not how the bump is. I need to ensure that the bump, so that bump that I drew there has the first 2 moments 0, maybe, if I am careful. Remember how I have this n and m? And n, I told you it's some huge number that I don't even want to talk about. That bump needs to have around n squared many 0 moments. So it's not that, okay? Integral of the function, the derivative of the function, the third derivative, they all have 0 mean. So how do you ensure that you have a compactly supported function of moment that you choose? So this is a question now that we're not going to continue until somebody tells me. If I tell you, design a compactly supported function which has the first 500 moments equal 0.
Use the
Yes?
Hermite polynomials.
Scott.
Yes,
No.
yes.
No. I disagree with Scott. It's one of the very few times we disagree.
So it seems like there's a lot of balancing of scales going on in this problem. Is there anything sort of about 3 dimensions in particular that's helping these things work out? Or do you kind of anticipate that like if someone was interested in like 7-dimensional Euler, that all of this construction would.
So these things are infinitely easier in higher dimensions. The higher the dimension, it's easier. The lower the dimension, it's harder. Nothing works in 2D because in 2D, two lines touch each other. 3D is the least dimension in which we can have two lines not touch each other. Okay, but to answer my own question, since nobody told me, take your favorite compactly supported bump and take 1,000 derivatives of it. Take Laplacian to the power 1,000 of it. Now that's a function which has the same support. It's also smooth, and it has 2,000 moments equal to 0. If you take a function and you take Laplacian to the 1,000 of that function, that's a new function. It has compact support. It's still smooth, and it has 2,000 moments equal to 0. And that's actually what we do. There's a comment I feel on the chat that maybe I should be made aware of.
Scott Armstrong. Okay, this is better than my suggestion.
Thank you, Scott. It takes a big man to acknowledge that. So we have something to work with now. So now we can finally roll off our sleeves and get to work.
I have a quick question.
Yes.
I don't know if it matters. Do you always take the same set of 6 vectors just for every Q or at any time that you do this?
Okay. So obviously there are countably many choices I could make. Is that true? How many rational points are on S2? Is it infinitely many or finitely many? Rational points on S2. I guess they're infinitely many, probably infinitely many. So there are countably many choices I could make of these 6 vectors. You could put if you want so the answer is it doesn't matter.
Okay,
But you could, if you want, put a probability distribution on the rational numbers on the unit sphere, maybe some kind of uniform measure, or maybe some Gaussian measure.
Sure.
Not uniform, some kind of Gaussian measure. Thank you, Jason. Yes, that was very stupid thing to say. And then you can pick randomly, and that also works, but it doesn't matter. I don't know what I was doing. I should go back here, but I feel like this board I should not erase. It has too much stuff. So I have to erase this board then. There's one more board. Now let's get to work. This is our Reynolds stress. So let's analyze the cancellation of the previous stress. So the cancellation we have just discussed occurs through the mean. So let's see what is the mean, what is the low frequency WQ+1 tensor WQ+1. Well, this is equal to, because these pipes don't touch each other, when I do the product, I'm not going to have sum over xi and xi prime of a xi w xi tensor a xi prime w xi prime. I'm not going to have that because xi needs to equal xi prime. That was one of my conditions that I wanted. So it's actually a single sum, and then I have the building block squared. The low frequency part of this has the mean here, which we have actually called something. This is xi tensor xi. That was one of the conditions, that the mean of this is xi tensor xi. So now linear algebra. Yes?
Isn't this a double sum?
So because of the support thing, it's a single sum. So linear algebra, if you give me any symmetric stress, symmetric 3x3 stress in 1/2 ball around the identity, there exist smooth functions, there exist xi's such that given any r, you can write r like this, some amplitudes. So the correct statement is there exist smooth functions gamma sub xi. No, let me start again. There exist 6 vectors xi which live on S2 intersect Q3, comma. There exist C infinity smooth functions gamma sub xi defined on the ball of radius 1/2 around the identity in the space of symmetric matrices, such that given any stress within the unit, the ball of radius 1/2 around the identity of symmetric matrices, you can decompose it like that with smooth functions. Okay, the proof is you can just write them down. Take the unit, take 3 vectors to be E1, E2, E3, do one more rational rotation, you're done. So that means that these functions A are somehow related to these C-infinity smooth functions gamma. Is our stress in the ball of radius 1/2 around the identity? No, our stress is small. We're trying to send it to 0, right? So what's happening here, it's a little bit of a trickery. Let's say the stress would actually be uniform, not just in L1, okay? Then what I could do is I could take the identity matrix, subtract the stress delta Q plus 1. Remember the size of this, let's say it were in an infinity, okay? Then the size of this is at most 1/2. And I can write this. And my lemma tells me that this is going to equal identity minus this. So if I choose amplitude functions to equal the following, summation over xi of a xi squared xi tensor xi is equal to what? Q plus 1 times that. We have canceled the stress, but we are left over with a multiple of the identity. Okay, what do we do with this multiple of identity? It seems like we can't cancel it. Keep in mind the divergence of an identity is a pressure gradient. So we just throw it in the pressure gradient. Now, of course, our stress is not L infinity. So it's not like I can just divide by delta Q plus 1 and I have a uniform bound. So what you really need to do is you need to take your stress and write it as a sum over its level sets. Okay, so maybe there's a sum over I, and then the piece of RQ, which is living between 2 to the I and 2 to the I plus 1. Okay, so level sets. Now that's a function of X and T, right? So here, instead of dividing by this, I need to say, well, characteristic function or some smooth version of the characteristic function of this level set times this, but I need to put a 2 to the I there. And what's going to happen is roughly the same thing, except instead of this, you're going to have a function of X and T, and it's going to have size this times 2 to the I. But that's okay, because the pressure is allowed to depend on X and T. You know, so that's okay. You can still hide it in the pressure. So that's how the cancellation of the previous stress works. Okay. So the only thing I'm not showing is how do you actually chop in level sets in a smooth way. We're going to talk about this a little bit. Any questions so far about just about the cancellation? The moral of the story is that these functions, if you think about its RQ dependence, if you think about the RQ dependence of these functions, they behave like RQ to the 1/2. That's what we're doing. We're taking the square root of a stress by writing it in this way. That's really what's happening. So it's the local level set version of the square root of RQ. Okay, whatever, and that's precisely what that means. In particular, the only reason I'm emphasizing on this, because it means that we know what the amplitude of this function has to be. Therefore, AXI in L2 and AXI in L infinity, look at this condition, the perturbation in L2. Perturbation in L2 is the L2 norm of that product. Everybody knows that the L2 norm of a product is the product of the L2 norms. Okay, that's true, because one function is slow and one function is fast. So the L2 norm of this is 1. We have made it equal 1. And the L2 norm of this is what I wrote here. So this thing imposes that, and this thing imposes that. Okay. So I guess we're down to homework number 4, which is again easy. It's an easy one.
Can I ask a question while you write it down?
Yes.
Do you ever need to worry about how big the pressure gets as you throw more and more stuff in it, or does it just do you never care because you only need to control the other pieces?
So there are some people in this field who always insist that one has to write estimates for the pressure. I'm not going to name names, but everybody who knows it's obvious what I mean. The pressure always is the solution of the Poisson equation. Laplacian of P is div W tensor W minus R. You don't need to do anything. The Ron-Zygmunt operator applied to that thing. Whatever you have, the pressure satisfies it automatically. You never have to write anything for the pressure. It's not the question, it's the people who estimate the pressure. So homework 4, given F, which is periodic, gradient to the n of F in L1 is less than some constant times lambda to the n. I would like to write instead of C sub F just the L1 norm of F, but that would be lying. Okay, so let's say there exists a constant F, and of course this is allowed to depend on n, but I'll be a bit more precise later what the n does. Okay, so assume we are given a function such that every derivative costs lambda, and we are given g, which is torus divided by, what notation did I use? Let me not screw this up. Okay, torus divided by kappa. I used the notation kappa. So I'm giving two functions. One is periodic at the unit size, and I know its derivative cost, and the other one's periodic at some smaller size. So if, okay, lambda to the 4, by the way, my box is minus pi to pi cubed. Lambda to the 4, 2 pi root 3, lambda to the m over kappa to the m is less or equal 1. M is a new number. So I want this to hold for all n less or equal n plus 4. Oh, nobody depends on n. Okay, because now I've specified something. So fg in L1 less or equal cf times g in L2. I have, I think, managed to write the lemma correctly. So this is homework 4. It's actually it may look strange, but it's very easy. And it's true. I've written it for L1. Similar things hold in all LPs. Okay. L1 is the easiest one. No. L infinity is the easiest one. Then L1 is the easier one. And then you get L2 for free by squaring and so on. Okay. Yeah, I'm not going to give hints. Am I done? Am I out of time? I was out of time 10 minutes ago. Okay, so we're going to finish this first lecture with the homework. I expect to be done by the next lecture.
Are there any other questions for Vlad? Had one?
Yes.
So I think you mentioned this already, and we'll probably see more in the last lecture. But can you mention again where the intermittency is in this construction and how it's going to be used to,
so far
get through to the lower the
only
the better regularity?
The only trace of intermittency you've seen so far is in the fact that I told you that these tubes, these pipes, they occupy a small volume in the torus.
Huh.
This RQ squared, which I mentioned, RQ is a small number. The fact that they occupy a small volume while still carrying unit L2 norm means they're not just concentrated, but also peaked. Prototypical function you have in mind when you think of intermittency.
Mm-hmm.
Where is it going to be used? In many places, everywhere in the proof. What I hope to convince you in the next lecture is that this number RQ, there's only one choice you can make. It's not arbitrary at all. There's only one choice you can make. And it's used in estimating things. And it's also used in dealing with not touching. Reason being that all these pipes, I'm slightly lying to you. Nothing is like what I said. That's the picture in Lagrangian coordinates. So in Eulerian coordinates, all those things are actually bent. So how am I going to make sure that they don't touch? I'm going to use some kind of pigeonhole argument. And that's where it's really nice that they occupy a small volume. So there's a combinatorial argument somewhere in the proof where once these pipes bend, the only way you can make sure that they don't touch still after they're bent, because you have the correct amount of sparseness or intermittency.
I see.
So it's going to matter there as well. It's not just in estimates. It's going to matter in the construction.
Combinatorial, yeah. So that limitation of beta 1/2 is.
Oh, I'll
is
show you where
coming
that limitation comes from.
I was just curious at a higher level, I think, whether your building blocks, you want to be stationary solutions of Euler. Is there any room to use more, let's say, non-trivial steady states? So things that aren't just sort of shears or sort of obviously, or even approximate steady states of Euler.
So in terms of approximate steady states, the error, let's say you have a master function, which is an approximate steady state. And then you say, I take this function, I put it at high frequency. If it's just approximate, the error you make is going to depend on Q. And it's hard to imagine that it's going to depend on Q in a very good way, unless you don't just do that. You don't just rescale it, unless you do something more to it, then rescale it. So yes, you could use approximate steady states, but then you wouldn't just rescale them and make them thin. You would have to do additional things to them. Second, could you use more complicated things which are just not even steady states? There are constructions like the Navier-Stokes construction that Rongchan mentioned. You actually cannot use steady states. That's a theorem. And so you have to use time-dependent solutions. And in those time-dependent solutions, imagine these pipes, there's a blob of fluid in these pipes, and the blob moves around the pipe somehow. And that's a time-dependent solution.
So this is for Navier-Stokes.
Yeah.
So you take sort of the viscously evolving steady state.
No. For Navier-Stokes, you treat the Laplacian as an error. What I'm saying is you don't use an Euler steady state, you use a solution of Euler with time. That's what I meant to say.
There's a question online from Scott Armstrong. You want to unmute yourself?
Yes, can you hear me okay?
Yes.
Okay, so maybe you said this already and I just didn't understand it when you said it, but are you putting the pipes only where the sort of gradient is nice so that you do have a kind of Lipschitz time scale? Because you only have an H1 velocity and not Lipschitz. And so you're going to put the pipe, I mean, is that what's happening?
I was going to mention in the next lecture. So these amplitude functions, I've always written A sub C of RQ and gradient VQ. And in terms of what I've convinced you so far is only how it depends on RQ. Like you need to chop it into level sets of RQ and then do something to it with these functions gamma sub xi. But actually then the dependence on VQ comes as follows. Gradient VQ is an L2 function. So you chop it off into level sets. Then for each level set, you have an L infinity function. And so for each level set, you have a different Lagrangian coordinate. These pipes, you put different sets of pipes at slightly different intermittencies. You put different sets of pipes in Lagrangian coordinates corresponding to every single different level set. And that makes these pipes dodging each other once they're being bent quite unpleasant, because if you smooth out two level sets, of course, they're going to overlap. And so it's kind of unpleasant. But the answer, Scott, is you put different pipes on every single different level set of gradient VQ. And so it's actually.
Thanks. I was just saying thanks. Sorry, it's hard not to interrupt when you're zooming here. Yeah.
Please interrupt.
Yeah, no, I was just saying I think that's a good explanation. It sounds like a difficult proof to write, though.
Yeah, but you have math.
Are there any other questions for Vlad? If not, let's thank him again.